Hello. In this part of the lecture, we're going to look at one circuit reduction technique called source transformation. Such technique is typically used in a circuit that involves more than one source. And for example, it can either be a voltage source or a current source. The technique can be used to convert all sources to one single type. For example, if I have one voltage source and one current source, I can convert the voltage source into a current source or vice versa. Source transformation is also performed between two circuit nodes, and this will be illustrated next. Lastly, this transformation changes only the source type. So for example, from voltage source to current source, or vice versa, while maintaining the circuit characteristic. Next, I wanted to show you a simple derivation to illustrate how you can correctly use this technique. There's one very important rule that you have to follow when you apply this technique. So what is shown here is I have this black box. So inside this black box, I have a circuit. Okay. And this black box is loaded externally with this resistor. So this is my so-called load resistor. So it's like some kind of loading, okay? And that loading is connected to this black box, which contains some circuits in it. Okay, so let's just assume that inside this black box, I have circuit number 1 and circuit number 2. So in circuit number 1, I have a simple voltage source connected in series with a resistor, which I call Rx. In circuit number 2, I have a current source, which I call Iy, and this is connected in parallel with another resistor called Ry. And notice that over here I use Ex instead of Vx, but so these two are equivalent. So E in this context is equivalent to the voltage source, as indicated by this symbol here. So external to this black box, I have this RL, okay, which is the same for both circuit number 1 and circuit number 2. Okay, so it's the same RL here, and then across this RL, I have my voltage drop, which I call VL. The current passing through this RL is my IL. So as far as this part is concerned, they're the same. Okay, so let's try to write down some simple equations that are known to us, okay, based on these two circuits. So first of all, I can find this VL. Again, this is the voltage drop across this resistor, and this can be simply found by just taking the voltage division. Okay? So I have this voltage source, EX, multiplied by RL over the sum. Now, similarly for IL, right? So I can apply Ohm's law. I can take this voltage divided by the sum of the two resistors. EX divided by RX plus RL. And finally, VL. So VL, I can simply again use Ohm's law. I can take the current IL times RL. Okay, so I can write down these simple equations to determine each of these parameters, VL and IL. Okay, I'm gonna do a similar thing here to circuit number 2. So I'm gonna write IL. So IL, I'm gonna use a simple current division because we know that we have this current source, and this current is going to be split into this resistor Ry and RL, depending on the weighting of this resistor sizes. Okay. So for example, for this IL, right, I take my Iy, and then I do the division here. I put, since I'm trying to find the current passing through this RL, so I'm going to put the other resistor on the top. Okay, so using this simple technique, I put this Ry on the top divided by the sum. Okay, so Ry over the sum. Okay. for VL, okay, so again, current passing through this resistor, which is IL, times RL, that will be my VL. And I can also rewrite it as, since we know that IL, okay, is equal to this, okay, so I can just simply replace this IL with this equation, okay, and then times RL again, right? Because we apply Ohm's law to find this voltage, to find this voltage drop VL. Okay, so we have written down all these equations, okay, that will help us understand or help us determine this VL and IL, okay, in these two circuits. So then the goal here, the objective here is we wanted to come up with a simple proof. Okay, we wanted to come up with a simple derivation to prove that this Rx, okay, and Ry, right? So this is my Rx and this is my Ry, are the same. Okay. So this is saying that if I wanted to translate, or if I wanted to transform circuit number 1 to circuit number 2, okay, I need to show that this Rx and Ry are the same, okay, so that this transformation is valid. Okay, so this is one very important rule that we have to follow when we apply this source transformation. But before we can do that, we need to go through this simple derivation just so that we understand why this is true, okay, or why this is valid. Okay, so I'm going to use this simple equations, okay, to guide us. Okay. So I'm going to evaluate, so I'm going to evaluate using two conditions. So the first condition is that I'm going to assume RL, which is this low resistor, okay, this low resistor here, is equal to 0, corresponding to a short. And then the second condition I'm going to apply here is I'm going to assume RL is equal to infinity. Okay, so this is equivalent to an open. And I'm going to apply RL equal to 0 and RL equal to infinity into both of these circuits. Okay, and then eventually we're going to draw some simple conclusion here. Okay, so when RL is equal to 0, okay, when RL is equal to 0, so this guy here is equal to 0, okay, so that means IL, the current IL, is simply equal to EX divided by RX. Right? So when RL is equal to 0, when this guy is equal to 0, means this here is shorted out. So the current passing through this short, if you will, is simply equal to EX divided by RX. Okay, so IL is equal to EX over RX. Okay, but at the same time, if we look at the second circuit, right? So this is circuit number 2. When RL is equal to 0, then remember current flows to path with the least resistance. So when RL is set to 0, then all of this current IY is going to flow into this short, and nothing is going to flow through this RY. Okay, so current flows to the path with the least resistance, right? So I have two paths here, so the lower of the two is this path, which is short. Okay. All right. So so that's why I was able to come up with this equation here. So IY, okay, IY is equal to IL, or IL is equal to IY. Okay. So I have this relationship here. So from here, I can rewrite it as this. I can say EX is equal to IY. Right? If I were to write this equation in terms of IY, I can use EX is equal to IY times RX, because I know IY and IL are the same. Okay, so that is my first equation. Okay, so far so good, right? So we're just going to do the same for the other case. So when RL, okay, the same RL is now equal to infinity. Okay, when this is equal to infinity, right? So we know when RL is equal to infinity, this corresponds to an open. Okay, So I'm going to again evaluate this condition using these two circuits. So when RL is equal to infinity, okay, first of all, when RL is equal to infinity, this guy here is open, right? So this is open. So that means VL, right? So VL, this VL here, okay, this VL here is equal to EX. Okay, so VL is equal to EX. Okay, so why is this equal to EX? Well, if this RL is an open, so that means no current is going through this open. In other words, IL is equal to 0. If IL is equal to 0, there will be no voltage drop across this Rx because there's no current passing through this Rx. So as a result, all of this Rx or all of this EX will have to show up across these two terminal, okay, as your VL. Okay, so one simple observation that I can make here is VL, okay, is equal to EX. Okay, so VL is equal to EX. Okay, so this is one simple observation that you can make just by looking at the first circuit. So now we're gonna do the same thing to the second circuit. So again, we set this RL to infinity. So when this guy now is open, so what happens to my voltage here, right? Well, so when this RL is open, so to evaluate this voltage drop, all I have to do is a simple Ohm's law, right? So I know the current, I know the resistor, so I times R will give me the voltage. So in this case, I have IY times RY, that will give me the VL. Okay, so again, this is just one equation, but this equation kind of, gives you the information coming from these two circuits. Okay, so I can just use one simple equation to describe this condition when RL is equal to infinity for both of these circuits. Okay, so now let's just equate. Okay, let's equate 1 and 2. Okay, so I have EX here, I have EX here, okay, and I have IY here, and I have IY there. Okay, so the only thing that is different between these two between these two equations is this Rx and the Ry. Okay, it's basically the resistance. Okay, one is based on Rx and the other one is based on Ry. Okay, so this tells us that from these two equations, in order for both equation 1 and 2, okay, to be the same, Rx and Ry, they have to be the same as well. Okay, in other words, they're forced, okay, to be the same, so that both equation 1 and equation 2, okay, are the same. Okay, so that this derivation is valid, right? So now I have this Rx and this Ry, right? So this tells us that this resistor in series and this resistor in parallel, they have to be the same numerically, okay, in order for this transformation to be valid. So if I were to transform, okay, the voltage source in series with a resistor, okay, into a current source in parallel with a resistor, what I have to make sure here is these two resistors have to be the same. If Rx is 10 ohm, then Ry has to be 10 ohm as well. Okay. And of course, we notice that this transformation allows you to go from voltage source to a current source, right? So how do we do that? Well, the relationship is simply based on Ohm's law, right? So we know that Rx and Ry are the same, right? And if we know the voltage, then we can calculate the current. So in other words, Iy, okay, is simply equal to Ex over Rx, okay, or Ry, right? Because Rx and Ry, they have to be the same, okay? So essentially, it's based on these two equations. Okay. I can say the opposite, right? I can say, well, if I want to transform this current source in parallel with this resistor into a voltage source with in series with a resistor, then all I have to do is I take Iy times Ry, okay, or times Rx, then I can get this Ex. Okay, so this is all based on just Ohm's law. Okay, the bottom line here, right? The one very important rule that you have to follow here is that I can only transform a series voltage source and a resistor into a parallel current source and a resistor. Okay, so series combination into parallel combination, but this series combination is the voltage source in series with resistor. Okay, so in other words, you cannot do something like this. If this is Ex and this is Rx, okay, and if you try to do, let's say this, okay, this is Ry and this is Iy, right? So if you try to do something like this, right? Notice the difference on the right here. I have voltage source in parallel with this resistor, and on the left here I have voltage source in series with a resistor. So if you try to convert from something in parallel, okay, into something in series like this, okay, going from a series voltage source and a resistor into, sorry, going from a parallel voltage source and a resistor into a series current source and a resistor, this will not work. Okay, so I'm going to put a big cross here. Okay, so this will not work, right? Because the derivation, okay, only allows, right? So you have to go through a derivation. So that this derivation here only shows that Rx and Ry are the same if you are using this configuration. And that's why, you know, in the beginning, we start out with these simple equations, okay, so which allows us to understand the relationship um, between the voltage and the current within each circuit. Okay, and from there we did the derivation, and then we arrive at this final condition. Okay, as a proof. Okay, so I'm gonna go over one example. Okay, just to show you how you go about using this technique correctly. Okay, so so in this first example, I have two sources, and I have one voltage source and one current source. And remember, you know, the idea of using this source transformation technique, which, you know, sometimes I just call it ST, right, for short, is that so we wanted to simplify our analysis, right? So if I can just keep the source, okay, um, in one type, right? So I can convert everything into a voltage source or current source, right? So perhaps that will help me simplify my analysis. Okay, so let's see how we can do something like that. Okay, in this example, so I have one voltage source on the right and one current source on the left. So what I'm going to do is that I'm going to perform source transformation, and I'm going to change this current source into a voltage source. And I'm going to follow, you know, my convention here as my template. And let's quickly go back to this template here. So this template tells me that if I have a series voltage and a resistor, I can convert this into a parallel current and a resistor. Okay. Now in this example, I have one parallel current source and a resistor. So that means I'm going to convert this into a series voltage source and a series resistor. Okay, so I'm gonna kind of go from the bottom to the top. Okay, so parallel combination to a series combination. I'm gonna change this current source into a voltage source while keeping Rx and Ry the same. Okay, so this is very important, right? Because I have this resistor here, and if you try to put this, back to the template, right? This is basically like your Ry. Okay, and I have this current source. Okay, so now I know that I have this parallel combination, so I'm going to convert it into a series combination consisting of a voltage source and a resistor. Okay, so Rx and Ry are the same, so I know that if I have a parallel resistor here, then I need to have a series resistor. Okay, if I follow the derivation, right? So I'm going to call this Ry and this one Rx, right? But this is just so that you can more easily follow or refer back to the derivation. But in reality, you don't have to say Rx or Ry, right? Because we know that there's only one resistor, and this resistor will be used over here. Okay. The only thing that you have to pay attention here is that this is going from a parallel combination to a series combination. Okay, so the resistor over here is now in series instead of parallel. Okay, and at the same time, I need to change or transform this current source into a voltage source. Okay, so now I have 3 amp and 4 ohm. Okay, so 3 times 4, based on Ohm's law, that will give me 12 volts. Okay, but then there is also this negative sign. Okay, so one simple way to keep track of this negative sign, right? Remember, let's just take a quick snapshot of this current source and the resistor. Notice that this current source is pointing downward. Okay, it is pointing downwards. So let's quickly go back to our template here. Our template here says what? So this current is pointing upward. Okay, so if this current, right? So imagine if this current is pointing upwards, so this current is going to flow into this Ry, right? Creating a plus here and a minus there. Okay, and this checks with the convention that we have over here for this voltage source. Plus on the top, minus on the bottom. Again, current source going into this resistor, creating a plus here on the top and minus here on the bottom, which checks with this polarity. Let's quickly go back to this example here. This current source is pointing downward. Okay, so this is first of all a flipped version of what you just saw. Okay, so if this is going up and I have plus here and minus there. Okay, so once I flipped, okay, this direction of the current flow, then I expect to see the, the opposite polarity, right? So now I will get minus on the top, okay, and plus on the bottom, okay. So in other words, I can draw it this way if I want to, right? So minus on the top and plus on the bottom, okay, and then I can put 12 volt like this, okay. Sometimes you say, okay, well, I don't want to have, this symbol looks a little weird, right? I'm more used to see plus on the top and minus on the bottom. That's fine. So if you wanted to do that, so what you need to do is you change the polarity and then you attach a negative sign. Okay, so you flip the polarity back to plus on the top and minus on the bottom, but you have to attach a negative sign. Okay, so instead of plus 12, so now you have negative 12. Okay, so remember every time when you change the polarity, okay, you have to attach a negative sign. Okay, similarly for the direction of current flow, anytime you flip the direction of the current, you have to attach a negative sign, right? Okay, so this is kind of the first exposure to this source transformation in circuit analysis, where we simply convert current source into the voltage source. Okay, so we now we're able to change all the sources into just one single type. Okay, so I have changed everything to the voltage source. Okay, this is the type of source that I want to see in this circuit. Okay, so I'm going to carry on with this part here. Okay, so of course the goal here is we need to find VO, right? So how do you find VO? Well, I can use nodal analysis, right? Or you can even use um, mesh analysis if you want to. Okay, so I'm using nodal analysis in this example. So we know that this is my V out, right? This is my ground. So VO minus negative 12. VO minus negative 12, right? Divided by the sum of these two resistors. Okay, the sum of these two resistances. So 2 plus 4. So I have 6. And I also have this branch, which is V0 minus 0 divided by 8, right? So simply just V0 over 8, and then V0 minus 12 divided by 3. Okay, so that's this branch over here. So 3 branches, 3 terms, okay? And of course, the algebraic sum, okay, will be equal to 0. Okay, so set to 0. And then you just solve for V0, that's all. Okay. Now, alternatively, right? So if you look at this guy here, right? Alternatively, what I can also do is I can change all the voltage sources into current source, right? So in other words, I have to do a source transformation um, here. Okay. So in other words, if I have 12 volts and 3 ohm, okay. So all I have to do, right? So go back to the template, right? So I can change from the series combination of a voltage source and a resistor into a parallel combination of a current source and the resistor. But notice that this is Rx and this is Ry, right? Notice that the same value, okay, for the resistance has to be used. Okay, so one is for Rx and the other one is for Ry, but we know Rx and Ry have to be the same, right? This is from the derivation that we just went through, okay? But for the current source, right, this is still based on Ohm's law. So if I know the voltage and then I know the resistance, then I can calculate the current 12 divided by 3. Okay, so then once you convert, say this part, okay, into something like this. So this is 3, this is 12 divided by 3, right? So V over R, so this is 4M, right? So then you basically just connect this part to this, and then you can, and of course, this will be gone. Okay, so connect here and connect there, right? That's how the source transformation was performed, okay? And then you can continue with your analysis. Okay. Okay. Let's look at the next example here. So again, this is still using the source transformation technique. Okay, so I have 3 sources. I have 1 voltage source and 2 current sources. Okay, so then the idea is I wanted to eventually calculate this current, which I call I naught. Okay, and this current is flowing through this 7 ohm resistor. Okay. And I wanted to make use of source transformation as much as possible, so that hopefully I can perform this circuit reduction. Okay, I can simplify the circuit as much as I can, so that hopefully, okay, it can be something as simple as a voltage source with 2 resistors, or a current source with 2 resistors, right? because if I can simplify my circuit down to that configuration, okay, or down to something that simple, then I can always use voltage division or current division to find the voltage or the current easily. Okay, so that's the idea, right? So again, the idea is I wanted to perform this source transformation, okay, as as um, as a way to simplify my circuit, right? To reduce my circuit down to something very, very simple so that I can use a very simple technique, simple as voltage division or current division to find the unknown parameter or variable of interest. Okay, so that's the idea here. Okay, and that's exactly what I'm gonna do. Okay, so now whenever you see an opportunity to reduce your circuits, okay, to combine some resistors, okay, you want to do that first. Okay, yes, that is also considered as a circuit reduction technique, right? It's something obvious and you can just combine, okay, simplify your circuit. So I see one opportunity here where I have 1 and 4 in series. Okay, 1 ohm and 4 ohm. So 1 plus 4, so I have 5 ohm here. Okay, so I can already combine these two immediately. Now similarly on the left, okay, I have 3 ohm in parallel with 5 amp in parallel with 6 ohm. Okay, now since all these three branches are in parallel, so it doesn't really matter how I place them. Okay, I can put this 5 amp over here in the front, okay, and I can even swap the position between 3 ohm and 6 ohm. Okay, doesn't matter, right? Because they are all considered in parallel, right? 3 branches in parallel, so I can move them around easily or randomly. That's fine as long as they're in parallel. Okay, so that said, I'm going to move this 5 amp to the left and then this 6 ohm to the middle. Okay, such that this 6 ohm and 3 ohm are in parallel. Okay, so in other words, this is what I did as an intermediate step. So 3, 6, and 5, right? So 5 amp to the left, all the way to the left, and I can now combine 6 and 3. So 6 in parallel with 3 is equal to 2. Okay, so far so good. I spotted something really obvious, right? So I can do that first, okay, before I carry on. Okay, so then the next step, right? So is that I wanted to start performing source transformation now. Okay, so what I'm going to do here is I'm going to transform these two. Okay, so I have a parallel combination of a resistor and a current source, so I know I can transform it into something like this. Okay, but remember the derivation says Rx and Ry have to be the same. So 2 ohm. So this resistor here remains 2 ohm. Okay. How about the voltage source? On the voltage source here, I apply simple Ohm's law, right? Take this 5 amp multiplied by 2, right? So I have I times R, okay? So 5 times 2, so this now becomes 10 volt. Okay. So I see another 5 volt here. Okay. I see another 5 volt here. And I know that this 5 volts, right? So if I were to include it over here, I basically have this is minus and then plus on the right, right? So this is actually my 5 volt sitting over here. Okay, and then this will go to the next component, right? So I have this minus and plus, okay, over here. So now I do see this opportunity where I can combine these two voltage sources together because they're in series. It's like batteries, right? You have your batteries, they're connected in series, right? You have, let me just redraw it. Oops. Excuse me. Hopefully this look like battery. Okay, so so basically, right, I have something like this. 5 volts, 10 volts, 10 volts, right? And they are all connected in series, plus minus, right? So then equivalently, I have 10 plus 5 or 5 plus 10, right? So okay, so I can just simply use one voltage source to represent this 5 volt and 10 volt in series. Okay, just think in terms of the battery, okay, that you use. Okay, so I have 10 plus 5 over here, just one single voltage source, and this 2 ohm resistor remains to be the same. Okay, so this is coming from this 2 ohm resistor. Okay, so far so good, right? So this is the simplification of the circuit reduction representing this portion of the circuit. Okay, this portion of the circuit. Okay, so then carrying on, I have 7 ohm resistor, and then this is still my I0, okay, I know, right? This part is the same, this part is the same, copy and paste, and then this is 5 ohm after the series combination. Okay, so what's next, right? So, well, I'm going to stick, right? So still I have two different source types. So I still have one voltage source and one current source. So I still need to change one of them into either a voltage source or current source. Okay. And if you look at the variable of interest, the variable of interest is I0, I naught, right? So perhaps it's easier for us to change this voltage source into a current source. And then perhaps, right, if the circuit reduction technique works, then we can probably just use a simple current division to find this current I0. Okay, so that's kind of the strategy here. Okay, so in other words, I have to convert the series combination of voltage source and a resistor into a pair combination of current source and a resistor. Okay, so I need to perform ST again. So I have 15 volt here, right? So 15 divided by 2, so I have 7.5 amp, right? And I have this 2 ohm resistor, so 2 ohm remains the same. Remember, Rx and Ry have to be the same, okay? But what's different here is I need to change the series configuration to parallel configuration, okay? Okay, so now this part is taken care of by this source transformation, ST. All right, and then on the right here, everything remains the same, 7 ohm, 3 amp, and then 5 ohm. All right, so then what's next? Well, so next, if you look at this circuit, right? So now I have 1, 2, 3, 4, 5. So 5 branches all in parallel, right? So now I do see another opportunity to combine the like components. For example, over here I see 2 ohm and 5 ohm in parallel, so I can immediately combine them. So I have 5 in parallel 2, and that will give me 1.4 ohm. Okay. So similarly over here, I have two current sources going in the same direction, and since they are in parallel, so I can simply just combine them, right? They're in the same direction. So imagine, right, this is coming from your KCL, right? So they're going in the same direction, going to the same node, and the current is going to add up. Okay, so I have 7.5 plus 3, and that will give me 10.5. Okay, so 10.5 in parallel with 1.43, and then in parallel with the 7 ohm. Okay, and where this is where this current I naught is flowing through. Okay, and of course, you may wonder, or some of you may wonder, why don't I also combine this 7 ohm resistor as part of this, simplification or circuit reduction? Well, the, the, the answer is, well, this is the variable of interest, right? So we wanted to find the current passing through this 7 ohm, right? So you actually don't want to include this as part of your parallel combination, okay? So you want to leave it there, right? So that you can use simple current division to find the current passing through the 7 ohm resistor. And that's exactly what's shown over here on the right, right? So to find this I naught, I simply just do a current division. So 10.5, okay, times 1.4 on the top, right? Because the current likes to flow to the path with this resistance. So you don't put 7 on the top, you put 1.4 on the top, okay? So 1.4 on the top divided by the sum. Okay, so you'll get about 1.8. Okay, so remember, if you can simplify your circuit down to something that involves only one current source and two resistors in parallel, okay, or one voltage source in series with two resistors. Okay, so let's say this is V, right? And then I can just simply use voltage division or current division to find the variable of interest. Okay, so this is the idea behind this source transformation technique. Right? The idea again is to try to simplify your circuit as much as you can, so that you can use a very simple circuit analysis technique, such as voltage division or current division to find the unknown. Okay, that's all. Okay, let's look at another example, and this is going to be the example that I'm going to use to also illustrate the next topic, okay, which is the Thevenin and the Norton equivalent circuit, okay? So I'm going to use this as a starting point, okay? It's still based on source transformation, okay, but I wanted to show you another two equivalent circuits that you will see um, um, and learn in this course. Okay? So circuit reduction using source transformation, okay? So that has been our goal, right? So the circuit given to you, okay, if you look at this, the circuit inside the dotted box, okay, inside the box, I have two sources, one voltage source and one current source, okay, and two resistors. This RL here is still my load resistor, okay, which I specify as 2 ohm. Okay. And the goal here is to eventually find what is the voltage drop across this 2 ohm resistor, which I call V naught, okay, V naught over here, or V out, okay. Okay, so then first thing first, so I'm gonna transform the 10 and the 5, right, 10 volt and the 5 ohm, using source transformation into the parallel combination of a current source and a resistor. Okay, right, so we have done this several times, so I'm going to transform this into this. 5 ohm remains the same, okay, Rx and Ry, right? And this current source is going to be 10 divided by 5. This is based on Ohm's law, right? So I have 2 amp over here. Okay, so far so good. We just did the transformation on this part using ST. The rest is the same. 4 amp, 3 ohm, RL, still the same, 2 ohm, okay, 2 ohm here, and this is still V naught, okay. All right, so next, right, now I have 3 branches in parallel, right? So remember, 2 current sources flowing in the same direction, I can easily combine them, 2 plus 4. Okay, no, 2 plus 4, right? So I have 6 over here, right? This is also another step of simplification. I can carry off one current source. Okay, so 6 amp, 5 ohm, 3 ohm, and then I have RL over here. So what I'm going to do next is I'm going to do source transformation again, right? Because this is a pair combination of current and the resistor. So I'm going to perform another ST so that I can convert it into a series voltage source and resistor. So 6 times 5, right? Ohm's law again. That'll give me 30 volts. 5 ohm remains the same, right? Rx and Ry thing, right? Okay, so I perform another transformation, and this is how I got this series combination or representation. 3 ohm here, 3 ohm there, RL remains the same. Okay, so far so good, right? So we just did a couple of source transformation and some simplification, that's all, right? All right, and then I do see another opportunity to combine the 5 and the 3, right? So 5 and 3 in series, so I can make it into 8 ohm, okay? So 8 ohm resistor, and this is 30 volts, okay? So one voltage source with 2 resistors. That's the perfect setting for me to use voltage division, right? Perfect setup, right? Because if I ask you to find V out, right? So V out can be found simply by using voltage division, right? This voltage divided by, this voltage multiplied by RL over the sum, okay? RL over the sum, okay? Times this voltage source, 30 volts. And we'll remember this number, and then we'll come back and revisit this result, okay? So V0 is equal to 6 volts, okay, using simple voltage division based on this circuit here. So if I arrive, okay, so let's quickly go back here. This is my starting point, right? This is my starting point. So if I go from here, okay, if I go from this circuit, okay, consisting of 4 components, 2 sources, 2 resistors, down to something that looks like this, where I only have 1 voltage source and 1 resistor, okay? Remember, only 1 voltage source and 1 resistor, nothing else, okay? If I were able, okay, to simplify my circuit from something like this, okay, and in reality, it can be more complicated than just 4 components. It can have, 6, 8, 10, or whatever, right? But the bottom line here is if I can come up with something, okay, to represent, okay, what I showed you earlier, right, by using these 2 components, okay, where I only have a voltage source and a resistor, okay, then this configuration down here, okay, is the so-called Thevenin equivalent circuit. Thevenin, okay, so this is a keyword, okay, so Thevenin, okay, Thevenin equivalent circuit. Ten volt, 4 amp, 5 ohm, 3 ohm, 4 components. I perform source transformation, circuit reduction, source transformation, finally arrive at something as simple as just 2 components, 1 voltage source and 1 resistor. But of course, the voltage source and the resistor are nowhere the same as what I had previously, right? So now this is 30 volts, this is 8 ohm. Before I have 10, 4, and 5, and 3, okay? They're not the same, right? But the idea is I come up with this source transformation, right? I use source transformation, and then I eventually arrive at this simple configuration consisting of only 2 components, okay? And this is the so-called Thevenin equivalent circuit, okay? The name, okay, the name that we use to represent this voltage source in the context of Thevenin equivalent circuit is VTH, okay, where TH stands for Thevenin. This is the so-called Thevenin equivalent voltage, or Thevenin voltage, in short, okay? And similarly, okay, I can also, okay, use the so-called VOC to represent the same thing, and I will explain why this is or why this can also be called VOC. Okay, so OC stands for open circuit. Okay, the open circuit voltage. This is VTH, Thevenin voltage, or Thevenin equivalent voltage. Okay, and this is equal to 30 volts numerically. And since we are talking about Thevenin, right? So this resistor, right, is also called Thevenin resistance, RTH. Okay, RTH, right? So we have VTH and we have RTH, only two components inside this Thevenin equivalent circuit. Okay, and together with this external RL as my loading, right? RL, then I can simply use voltage division to find this VO. Okay, or V naught. Okay, so that's the Thevenin equivalent circuit. There is another configuration also consists of only two components, and that's the so-called Norton. Okay, so Norton equivalent circuit. Okay, one is Thevenin here, and the other one is Norton. In a Norton equivalent circuit, what we have is so again, inside this dotted box, I have only two components. One is the current source, and the other one is the resistor. And notice that this current source and this resistor are in parallel. Okay, or they are in parallel. Okay, and this resistor here, R sub n, right? This is my Norton resistance. And the current, okay, over here is I sub n. Okay, this is my Norton current, IN. And this IN, right, is also called ISC, okay, where SC stands for short circuit. Okay, so this is like my short circuit current. This is my open circuit voltage. Okay, so VOC and ISC. Okay, and we know that ISC can be found by, right? So if you, right, so this should hopefully remind you, right? I can perform source transformation here, right? Because I have a series combination here, I can convert into parallel combination, okay? So this current source is equal to VTH divided by RTH, okay? And right, if you recall, this is 8 ohm, and this also has to be 8 ohm because RN and RTH, they have to be the same, right? Just like the story we talked about, RX and RY have to be the same, okay, in the derivation. Okay, so RN and RTH. Okay, so 8 ohm and 8 ohm. Okay, and so remember, this is one current source together with two resistors in parallel, right? So I can simply just use current division to find the current passing through this RL, okay, and take that current multiplied by this RL to find the V out. Okay, so that's the technique that you can use to find the voltage using this Norton equivalent circuit. Okay, so let's look at one example, okay? And this example is actually the same as the very first example that I show you over here. Okay, so we're gonna take this exact same circuit, copy and paste. Okay, so 10, 4, 5, 3. Okay, so take this circuit and then put it down here. And we are going to analyze the circuit using the Thevenin equivalent circuit approach. Okay, for our first example. Okay, and then in the second example, we're going to do the same, except we're going to use Norton equivalent circuit. And hopefully, if we do everything right, you're going to see exactly the same answer, okay, for the V out. Okay, and let me remind you, right? So the V naught that we found from this source transformation approach is 6 volts, right? So we have to sort of go back and make sure we obtain the same number here. Okay. All right, so let's look at how we can perform Thevenin equivalent circuit on this circuit. Okay, so two sources, two resistors, the same load resistor, 2 ohm, no change. Okay, and the current passing through this load resistor is something I call IL. Okay, it's IL, right? L stands for the load. Okay, load current. All right. So first of all, in order for me to simplify this circuit, okay, into, right, remember this is Thevenin equivalent circuit, right? So the goal here is I wanted to come up with something. This is RL, right, 2 ohm, okay, and this is VO, okay, VO. That looks like just like this, right? I wanted to sort of condense my circuit down to something with a voltage source and a current, voltage source and a resistor, VTH and RTH. That's all. Okay, that's what I'm trying to achieve here. Okay. So to do that, I need to find this VTH. Okay, and this VTH earlier I mentioned that this is also called VOC, where VOC stands for open circuit voltage. Okay, so then I'm gonna go to my first step here. Okay, it's the first step. What I need to do is I need to open circuit the load. Okay, so assuming, for a second, right, for this first step, that this load RL, okay, is now opened up, right? It now becomes an open circuit, meaning I can simply just cross this one. Infinitely large resistance, right, which is your open, right? Which is like an open circuit, okay? If I have an open circuit here, then that means there is no current flowing through that open. And as a result, IL, okay, is equal to 0, right? Current cannot go through an open circuit, right? So IL is equal to 0. After setting this condition, right? So again, the goal is we wanted to find this VOC, right? So to find VOC, the procedure is that you need to open circuit the load, okay? Open circuit the load. And when the load is open, then we know that there is no load current, okay? And then we find that VOC, okay? And that VOC, okay, is this VOC over there, which is the same as VTH, okay? So by applying this condition, if we can find VOC, then we can identify already one of the two components inside this box. And then, of course, the next one is, or the last one, right, is to find the RTH. Then we are done, okay? So let's look at how we can find this VOC. Okay, so when this guy here is open, right, when RL is open circuited, then this is VOC. And remember, IL is equal to 0. So if IL is equal to 0, no current, okay? So that means no voltage drop across this 3 ohm resistor. Right? You guys see this, right? So IL is equal to 0. No voltage drop across the 3 ohm. Okay. If there is no voltage drop across this 3 ohm resistor, so that means I can move this VOC, right? So my VOC before was here, so now I can move this VOC over to here. So over to here, this is my this is my VOC. Okay, so in other words, VOC is actually the voltage drop across this current source. Right? So in other words, I can do it like this. And so again, IL is equal to 0. If IL is equal to 0, then no current is passing through this 3 ohm resistor. If no current is passing through the 3 ohm resistor, then that means no voltage drop across the 3 ohm. So if there's no voltage drop, then that means this VOC, before you're sitting over here, I can move them to here. I can move it to here. No problem. Okay. So that means if we know the VOC across or the voltage across this 4 amp current source, then we know the VOC. Okay. So the step here, right, that I'm gonna, or the the step here or the technique here I'm going to use is going to be KVL. Okay, so KVL, right? So I have 10 volts, which is this 10 volt here. Okay, so 10 volts. Right, so if I assume the current, right, convention is going this way, right? So 10 volts is equal to, right? So I'm supposed to get this current, if I call this current I, so I should get I times phi I, right? For the voltage drop, okay? But notice that I have this current source, okay? And that is going in the opposite direction as how I define this current I, right? So this 4M is actually going in the opposite direction, okay? So if I is going clockwise, then 4M is going in the opposite direction, then that means this I is equal to -4, okay? So in other words, the voltage drop across this 5 ohm resistor, right? I have -4 times 5, okay? And then plus VOC. Where is VOC again? Right. So VOC is the voltage drop across this current source. So I have this voltage is equal to this voltage. Okay, the voltage drop across 5 ohm, and then plus this voltage across this 4 amp current source, which is VOC. Okay, it's a simple KVL equation, right? So we just need to solve for VOC. Turns out to be 30 volts. Okay. All right, so I probably wanted to clean up this part a little so that I can show you the next. Well, actually, I have the drawing here, so I can reuse this. Okay, I'm gonna leave the marking here. All right, so the next step is to find RTH. Let's quickly go back to revisit this this little Thevenin equivalence. So we just found VOC, and we know VOC is equal to VTH. The only component that we need to find is RTH so that we can complete the our mission here. Okay. So RTH is the Thevenin resistance. And to find this Thevenin resistance, what you need to do here is you need to deactivate, okay? You need to deactivate all the sources. Okay, so we have a voltage source and a current source. And remember in the in a lecture where we talked about superposition, to deactivate the sources, we have to zero out, okay? We have to zero out the current source and the voltage source. So when we deactivate a voltage source, we know that the voltage source will be shorted, okay? And we can represent by a short. And for current source, it'll be represented by, it'll be replaced by an open, okay? So we do that. We short the voltage source. Okay, so we short the voltage source and we open the current source, right? So to open the current source, I simply just cross it out, okay? Right, so now, so if you look at this circuit here, it's basically the same, right? So I have 5 ohm here, 3 ohm there, and this is my RL, okay? So what is RTH, okay? So the definition of this RTH is that I wanted you to imagine that you're this resistor RL over here, okay? So it's like you're standing right here, and you look all around you, okay, in all directions, top, bottom, right, and left, okay? And you want to capture all the things that you see, okay? But before then, you have to deactivate all the sources, okay? And then you look at what is left, okay? So in this case, I have 3 ohm and 5 ohm, okay, on the left, right? So when you look this way, okay, you see 3 and 5, okay? And we know that 3 ohm and 5 ohm are in series, okay? So as a result, right, this RTH is simply just 8 ohm. Okay, so again, to find this RTH, imagine you are standing right here, right? You're this RL, okay? So you look all around you, okay? You look to the right, look to the top, and look down, right? So When you look up, you don't see anything. When you look down, you also don't see anything. Okay, you don't see yourself. Okay, when you look to the right, you also don't see anything. But when you look to the left, okay, again, you are this RL, right? So you don't see yourself, okay? But you see 3 ohm and 5 ohm in series, okay? When you look to the left, okay? Imagine you're this RL, right? So you don't see yourself, right? So you don't count this RL as part of this RTH, okay? So when you look into the left, you see 3 and 5, right? So I combine them. So in terms of RTH, this is what I observed, right? 8 ohm. Okay. Putting everything together, so VOC 30 volts, okay? RTH 8 ohm, right? So as far as this part is concerned, this is my Thevenin equivalent circuit. This Thevenin equivalent circuit now is loaded by this RL, which is 2 ohm, right? This is part of the example, right? The question given to you, okay? So you cannot change the load. Once it's given, specified, right? You cannot change it arbitrarily, okay? So now, all we have to do is to find this VL, right, or VO, whatever we call it earlier, right? The bottom line is we need to find what is the voltage drop across this RL, right? So simple voltage division will do, okay? So VL is equal to 30 times 2 over the sum. Surprisingly and not surprisingly, right? So we got 6 volts again, which checks with the result that we obtained from this pure source transformation technique. Okay, so this VO, right, or VL is equal to 6 volts. Okay, let's look at the same example, or the same circuit using Norton equivalent circuit technique. Okay, so this is the second example, right? Using the same circuit, okay, 10 volts, 4 amp, 5 ohm, 3 ohm. Okay. But now I'm going to use Norton equivalent circuit. Okay, and we remember that in Norton equivalent circuit, the configuration, it looks something like this. This is RL, and this is RN, right? And this is IN, which is the same as ISC, okay? Where ISC stands for short circuit, okay? Short circuit current or Norton current. Well, and in fact, even without doing much, right, you can sort of already deduce that this Rn has to be equal to 8 ohm, right? It has to be equal to RTH, right? So this is the outcome of the source transformation, right? So we um, we saw the derivation earlier, about this Rx and Ry. Right? They have to be the same. So RTH and Rn, they have to be the same as well. So 8 ohm. Okay. So we'll see the same step in a second. Okay, so now let's try to figure out this ISC, right? So as the first step here, I need to short circuit the load. Okay, instead of open circuit the load, okay, like in the first example, now we need to short circuit the load. So to short circuit the load, I set this RL to 0. I set this RL to 0. Right? So let's set it over here. It's short. Okay. So I short this load and I need to find, right? So when I short circuit the load, remember VL now becomes 0. Okay. This just for this first step. Okay. Because this is my VL, right? So when I have a short here, VL becomes 0, right? So this is something that we can easily say, right? Okay. All right. So VL is equal to 0. So now we need to find ISC. So where is ISC, right? So ISC, okay, is the current passing through this short, okay? And this is the same as IN, right? So this is from here. Okay, I'm just showing you the full picture here. So ISC or IN, right? And I know that I'm probably going to use mesh analysis to solve this problem, okay? And I know that I have two loops, okay? So, and in this second loop, I'm gonna call this I2, right? So that's why I say, oh, okay, this IC is equal to IN, and it has to be equal to I2 as well. Okay, so I have ISC, which I need to find, right? So if I know I2, I know ISC. Okay, so then it comes down to just solving the I2 using mesh analysis. Okay, and if you look at this circuit, right? So I have this 4M current source stuck between two loops. Okay, so that indicates that I have to use super mesh. Okay, so super mesh. Okay. So I have a shared current source between the two loops. Okay, between these two loops, I1 and I2. So now I have to use super mesh. Okay. So which is fine, right? Because we know how to use super mesh from last time. So I have this 10 volts, okay, and 10 volts is equal to I1 times 5. Okay, so this voltage drop. And since I know there is this current, okay, stuck in between, okay. So now I have to move to the other loop, okay. So I use I2 times 3, okay. So I have I1 times 5 and then plus I2 times 3, okay. So those are the two voltage drops, okay. And at the same time, because I need another equation, right? Because I'm applying super mesh, so I need to have this another equation so that I can solve for two unknowns, okay, two equations and two unknowns. Okay, so in other words, I know this is I1 and then this is I2. Okay, so and I know this 4M is going upward, so I know I can write it this way: I1 plus I4 plus 4, okay, is equal to I2. Okay, so in other words, I1 is equal to I2 minus 4, right? So move the 4 to the other side. Okay, so now I have two equations, one here and two here. So two equations, two unknowns. No, so now we can solve for I1 and I2, right? But I2 is what we are interested in. Okay, so I2 turns out to be 30 over 8 M, right? M. Okay. All right, so since we just found I2, right? So we can now easily deduce that or equate, right? IN and ISC over here as well, right? So IN and ISC are both equal to 30 over 8, okay? 30 over 8. Okay, so how about RTH? Well, same thing. So we have this resistor here, okay? So it's the same circuit, right? So now I have to probably go back to this circuit again, right? So it's exactly the same circuit. We have to perform this deactivation thing, right? So we deactivate all the sources, voltage source we shorted, current source we opened it, right? So and you imagine your this resistor standing right here. You look all around you. When you look to the left, you see 3 and 5 in series. Okay, exactly the same step, right? So the step of finding RTH and RN, okay, in both examples, example 1 and 2, are exactly the same. Okay, so that's why I can easily say this is 8 ohm. Okay, so RTH and RN are the same, so this is equal to 8 ohm. And I have my Norton equivalent circuit, which consists of a current source in parallel with a resistor. Okay, and notice that this resistor, this is my load resistor, it remains the same, right? This one I cannot change. Okay, it's always 2 ohm. And this is my V naught. Okay, so to find V naught or VL, simple current division first. Okay, to find the current passing through this 2 ohm resistor. Okay, let's say this is my I, and this is this I here. So I take this current, multiply by 8 over the sum. Okay, 8 ohm over the sum. So that's this current passing through this 2 ohm resistor. Take this current, multiply by the resistor, okay, which is 2 ohm. Okay, so I times R. Okay, so I get 6 volt. Okay, so again, I got exactly the same answer just as before. Okay, so 6 volt here from Norton equivalent circuit, 6 volts from Thevenin equivalent circuit, and then lastly 6 volts again using source transformation. Right, so everything checked. Okay, if you do everything right, these three should give you exactly the same answer. Okay, Thevenin and Norton. Okay, so we'll do one more example just to wrap up. Okay, so last example, find Thevenin equivalent circuits and use source transformation to find Norton. Okay, right, or vice versa, right? So if you feel more comfortable finding Norton equivalent circuit, you can do the source transformation on that to get to the Thevenin. Okay, but in this case, I'm going from Thevenin to Norton. Okay, so I invite you to try out um, on your own. Okay, so to find Thevenin, right? So we need to find VOC or VTH. Okay, so to find VOC or VTH, we need to open circuit the load. Okay, so this is now open. Open circuit. Okay, open the load, and then IL is equal to 0. Okay, so IL is equal to 0. All right, so let's see. So I need to find VOC here, right? So this is my VOC. So VOC, this is my VOC, right? Because there's nothing connected to here. So this is my VOC, this is my VOC. So my VOC is basically the voltage drop across 5 ohm resistor. Okay, so let's see. So I wanted to first find, right? So the approach that I took here is I wanted to first find this Vx. And once I know this Vx, I can do a simple voltage division to find this VOC. Right, so this is my Vx, right? So you can see that this is Vx, this is 8 ohm, this is 5 ohm. VOC is the voltage drop across 5 ohm resistor. So if I know Vx, I can simply use voltage division to find the voltage drop across 5 ohm resistor, which is my VOC. Then I'm done. Okay. So then the question is, how do we find Vx first? Okay. So simple nodal analysis will do. Okay. So Vx minus 12 divided by 4. So that's this current. Okay. Plus negative 2, right? So I flip the directional current, okay, and I have to attach a negative sign. Okay, so minus 2 going this way out, okay, out of the node. All right, and then plus Vx minus 0, okay, so I go all the way to 0, okay, divided by the sum of 8 and 5, okay. So Vx minus this voltage divided by 13. Okay, so 3 branches, right? So sum all of them to 0, KCL, right? This is based on KCL because we are doing nodal analysis. Okay, all right, so then once we found Vx, then the next step, right, is to use voltage division to find VOC, that's all, right? So VTH or VOC is equal to Vx times phi over the sum, right? Simple voltage division again, right, as I mentioned. So this is 5.9 volt. Okay, based on voltage division. Okay. All right. So next step is to find RTH. So to find RTH, remember we have to deactivate the sources. So I have one current source and one voltage source. For the voltage source, I need to short it. And for the current source, I need to open it. Okay. So now it comes down to something like this, right? So remember, you are this, so this is my RL. I'm going to put it back here. So you're this RL. okay, standing right here, and you look all around you, okay, in every single direction. So you look up, you look to the right, so you look down, right, you don't see anything. But when you look to the left, okay, you see something, right? But again, imagine you're this RL, right? So you don't see yourself. So when you look to the left, right, you see this chunk over here, okay? So you simplify the circuit, right? You always simplify the circuit that is furthest out, okay? So 8 and 4 are in series, okay? And then in parallel with 5, right? So 8 in series with 4 first, and then in parallel with 5, okay? So that's what you see when you're sending right here, okay? For you, as you know, to find your RTH, okay? So 3.5 ohm. Okay, so then of course, very last step, put everything together. You have the BTH or VOC that we just found, and also RTH that we found over here, and you put everything back into this series combination, okay, for the Thevenin equivalent circuit. Okay, then you're done, right? And of course, if I ask you to find V out, right, then you will do voltage division. Okay, so that's something that we have already um, done and justified earlier. So, but then the second part of the question is you need to convert it into Norton equivalent circuit, right? So this part here is pretty straightforward because we know how to use source transformation already. Okay, so we can go from Thevenin to Norton quite easily by performing ST. Okay, so I have ISC, IN, which is simply just taking this voltage source divided by the resistor. Okay, so 5.88 divided by 3.53. Okay, and then in parallel with this resistor, RTH, okay, with a resistance of 3.5 ohm. Okay, same resistance. Okay, 3.5 and 3.5. RTH and R are the same. Okay,